Okay, we are talking about the matrix approach to linear regression model. Okay, in the previous class, I explained already. For example, this is the equation for population regression functions. We have sample from the first until the end, first one to until the end. The sample size is like this one. Here, I is a sample size from 1 until n. Okay. We can divide the equation by sample. This one is the first sample here. Y1 is equal to beta 1 plus beta 2 x2 1. Okay, the first two here is referred to the variable name, variable number, and the second number here is a sample size, the sample subsequent sample, the first sample. Okay, same as to x3, we have number 3 here for the third variables, and we have first sample here until bk xk1, and we can also write down here for the second sample here, the second sample here. Y2 is equal to beta 1 plus beta 2 x2 2 until beta kxk2 plus residual, second residual. And if we write down here from the first sample until the end sample, we can write like this. And then we arrange this equation C12 into matrix notations as C13 here. Here, we have y is n by 1 column vector, and we have x is n by k. We have n samples and k explanatory variables. And then here beta is a column vector, k by 1, and we have residual n by 1. Okay, here n by 1 column vector of observations of dependent variable is y here. X is n by k. We have k independent variables or explanatory variables. Okay, beta is a column vector of unknown parameters. We use this equation to calculate the betas. Mu is residual as a column n by 1. Okay, and from the equation C13 here, we can write down in compactum here like this, C14. Y is equal to x beta plus residuals. This is multiple regression model in matrix notations. Okay, in compact, here we can write down is y is x beta plus mu is residual. Okay, before we continue with this, we talking about the classical linear regression assumptions in matrix notation. Okay, the assumptions of classical linear regression in matrix notations. Okay, we have here when in scalar notations and matrix notations. First, in matrix notation, expected value of residual is 0. Okay, we can write down like here. Expected value is mu is 0. This means the mean value of residual is 0. Okay, and then we have expected value of mu time mu prime is sigma square I. Here in equation in assumption number 2, we have two assumptions here. Okay, the first about the we can write down here expected value of mu prime mu is equal to sigma square. Here we have constant variance. Or in other word is homoscedasticity. If we have I and j here, for I is equal to j. Here we can write out this I is equal to j. Okay. This is assumption of homoscedasticity. And another one is expected value of mu prime is equal to here is equal to 0 here. This assumption about no serial correlation, no serial correlations exist between the residuals for I is not equal to G. Here the orthogonal assumptions. Okay, this in the second assumption, this assumption has two properties here. First is a constant variant, another one is no serial correlation exists. And the third assumption is the n by k matrix X is non-stochastic. That is the samples are fixed in repeated sampling. This means there is no correlations between the independent variable or explanatory variable with the residuals. Okay, this is the most important assumptions in the classical linear regression model. The expected value of x prime mu is equal to 0. This means that no correlations in explanatory variable with the okay, or in other words, the x variables are non-independent. This is the most important assumption in the classical regression model. Okay, and also we have here the fourth assumptions. The rank of matrix X is K. K is a number of explanatory variables. This assumption state that okay, there is no exact multicollinearity among the independent variables. Okay, exact multicollinearity among the variables. We stated in metric notation that rank matrix X, the X okay, is the number of variables. Okay, to guarantee that the expected parameter can be calculated by using the data. Okay, here and number 5. The residuals are normally distributed with zero mean and constant variance. Okay, usually in midterm tests, we have these questions about metric notations of classical linear regression assumptions. Okay, this is the variant covariant matrix. We have here. This is a variant for beta 1. This is a variant for beta beta 2 until variant for beta k. Okay. This is a covariant. Covariant we assume is 0. Okay. And how we calculate the parameters by using matrix approach. Okay. Now we have this equation C31, and we can simply simplify the model like C32. Okay. We know in the matrix notations we have residual is equal to actual value dependent variable minus with the expected, the predicted value. This is a residual. Okay, in terms of matrix notations, we can write down like this. Okay, this is we have this estimated equations, and then we calculate the residual, the difference between real value and predicted value. We get this one. Okay, this one is residual. Residual is a difference between real value and expected value, predicted value. And then because the approach is ordinary least square, so the equation C36 to be square become equations C37. Okay, this is a square. Okay, let me explain this one. Okay, I explained already in matrix notations. Okay, this one y has prime here, so we multiply y prime y, we get this y prime y. Y prime y is equal to sigma y square. Okay, this one minus 2 come from first we multiply y prime with x beta head. Okay, and another one we multiply minus x beta, because here there is a prime here, become beta prime x prime y. So we can summations y prime x beta head and beta prime x prime y. Because this is a scalar, so we can get 2 times of the same thing. So we can we get this one minus 2 beta head prime x prime y. Here we multiply minus x beta prime. Okay, because x beta prime, I can show you the multiplications in matrix notations. Okay, I explained already. This one is, for example, a prime beta prime become beta b prime a. Okay, if b is in the last, become the first, then a is the first, become the last. In the first term here, we have prime here, and we get another prime, become a without prime. The b without prime, but after we prime is become beta prime a. So here we can see the multiplication between x minus x beta head prime become beta prime x prime. Okay, x. Okay, we multiply this one with this one, beta prime one. Yeah. Okay, this is beta prime time x prime from here. Okay, and x here. Okay, here we have x here. Yeah. Sorry, this one. Okay, and then we get beta. Okay, here there is explanation. Beta prime x prime y is a scalar, a real number. It is equal to its transpose. This means y prime x beta. Because this is a scalar, we can summation these two parts. Okay. Okay. First, we have to derive this. We take the derivative of this equation C37 here. Okay. Okay. From the 3. Sorry, C37. Okay. Here we have beta. Derivative of beta is 1 because beta to the power 1. Okay, so we get minus 2x prime y. Here we have two betas. Yeah, this one beta, first beta here. There is another beta in the last position. So this means beta prime beta become sigma beta square. If we take the derivations of beta prime x beta become 2 times x prime x beta. Okay, we get here. Yeah, x prime x beta is equal to x prime y because x prime x beta has 2 and x prime y also has 2. So 2 by 2 is equal to 1. And in metric notation, there is no division in symmetric notations. So we multiply equations C310 with x prime x inverse. Here, because we multiply x prime x inverse in the left side of the first equations, so we also multiply the equation C310 by x prime x inverse in the left side of the second part of C310. So become x prime x inverse x prime y. Okay, in a matrix, x prime x inverse multiplied by x prime x is equal to identity matrix. This one. Okay, identity matrix times beta itself. Identity matrix multiplied by any matrix become the original matrix because we multiply identity matrix with beta, we get the beta itself. So beta become x prime x inverse x prime y. So how to calculate the betas from the equation C311 is the formula to calculate the beta value or the parameter of the regression equations. So don't forget, for the formula of beta hat is x prime x inverse x prime y. Any question? No any question? Okay, let me explain by this example. Okay, we have only two here, beta 1 and beta 2. So we have here x prime x. So we have x and we prime, the rows become columns and the column become the rows. Okay, here 1 times 1 plus 1 times 1 plus until 1 times 1. We get n here, number of sample. So the component of x prime x is n, the first element 1, 1. And the second here, sigma xi, because we multiply 1 with x1 plus 1 with x2 plus 1 x3 until 1 xn. That means we get sigma xi. Here we multiply same thing, x1 we multiply by 1, x2 with 1, x3 with 1, until xn with 1, we get sigma x. And the last one is x prime x x1 times x1 plus x2 times x2 until xn plus times xn. This means we get sigma x squared. So the xy is we multiply x prime y, because we have here one is the constant for the intercept of the equation, and x1 x2 until xn the value of first variables. Okay, we multiply 1 with y1 plus 1 with y2 plus 1 with y3, we get sigma y. And we multiply x1 with y1, x2 with y2, x3 with y3, until xn with yn, we get sigma xy. So after calculation this, we insert into this equation, x prime x is a 10, 10 is a number of sample, 1700 is sigma x, and 322,000 is sigma x squared. And we multiply xy, this is sigma y, and this 1110 is sigma y, and 205500 is sigma xy. Okay, the inverse. Okay, how to calculate inverse? Okay, from here, we calculate first is determinant. Determinant is, okay, here let me show you how to calculate the okay, we have this. Okay, let me clear up this one. Okay, we have x prime x. X prime x is equal to, okay, with matrix notation. Okay, we here 10, 700, and here 700. This one to get the better appearance. 322. Sorry. Okay. Now, okay. Here. Okay, and then okay, we have this x by x prime x. Okay, and we calculate the determinant. X prime x is equal to, okay, 10 multiplied by, okay, 322,000 minus 700 times 700. Okay, can you calculate it? What is the determinant of x prime x? Okay, 700 times 700, we get 299. Okay, 2890,000.
29,310,000.
The result.
I think so.
Right.
Wait.
Okay. Okay, we have 10 times 32200 minus 2x90. What is the value?
300.
330. 330.
910,000.
30,000.
Like this.
130,000, yeah.
Okay. 30,000.
310,000.
10,000, sir.
Huh? 10?
10,000.
No. Are you sure?
Yes, sir.
Okay, let me show you. We can calculate this one. Okay. We have read A, rows is equal to 2, column is equal to 2. We have 10, 700, 700, and 322, 000, right? Matrix determinant A is equal to that A. I'm sorry. Print that A. Okay. Okay, we have the double 3 quarter 0, right? Okay. So this is the correct answer. Okay. And then this is a determinant. Okay. And then we can calculate the inverse. Okay, let me show you the inverse here. Okay. Matrix inverse is equal to inverse A. Means A inverse. Okay. And this is the determinant. No, in the inverse of matrix A. Can you get it? Okay. We calculate here the first, okay, main diagonal. Main diagonal replace change place for the main diagonal. This means 322 000 become element 11, A11, and 10 become element 22. And off diagonal become negative. From positive become negative, and from negative become positive. So here, okay, we get here the determinant and the inverse. Okay, so we calculate the inverse is A inverse. A inverse is equal to here x prime x inverse. Okay, we get x prime x inverse is equal to 1 over determinant x prime x times adjoint x prime x. This means we have here equal to 1 over 33,000 multiplied by adjoint x prime x. Okay, adjoint x prime x. Okay, let me write down in here. Okay, here it's equal to 1 over 1,000 multiplied by adjoint. Adjoint A is adjoint x prime x is equal to 32. Okay. And minus 1700. Yeah, minus 1700. And 10. Yeah. You get it? Okay, sorry for bad drawing. Okay, you get it now?
Yes, sir.
Okay, and we get the results is equal to this one. Okay, 0.975 something. Okay, and the second first row, second column is minus 0.0051 something, and etc. Okay, and then we multiply with x prime y. Here x prime y is 11110 and 20550. Here we get this inverse. This is inverse is the number we get from the calculations, and beta is we multiply x prime x inverse with x prime y. We get beta 1 is 24 point something, and beta 2 is 0.5079. Okay, this is if you have 3 by 3, that means you get beta 1, beta 2, and beta 3. If you have 4 by 4, that means you have beta 1, beta 2, beta 3, and beta 4. Any question? No? Okay.
No, sir.
Okay. And variant covariant matrix. Okay. This is variant covariant matrix. We get here variant beta 1, variant beta 2, and variant beta k. This covariant. If we take square root of variant beta 1, we get standard error of beta 1. If we take standard square root of variant beta 2, we get standard error beta 2. How to calculate the variant covariant matrix is sigma square multiplied by x prime x inverse. How to calculate sigma square? Sigma square is y prime y minus beta prime x prime y over n minus k. This is mu prime mu is y prime y minus beta prime x prime y. If we divide it by n minus k, we get sigma square. Okay, sigma square is mu prime mu over n minus k. Okay. Okay. Y prime y minus beta prime x prime y is equal to mu prime mu. Any question? No any question? You get it? Okay. If you have any questions, no any question, we can continue with this r square. Is a coefficient of determination. Is a beta prime x prime y minus n y bar square over n y prime y minus n time y bar square. Okay. Now we can calculate for the 3 by 3 data. Okay, we can take chapter X, for example. Let's finish for metric, metric approach for to multiple regression model. Okay, this mean we have here. Okay, chapter 7. Okay, we have okay, demand for money. Okay, here the data. Okay, demand for money. This is 7-Eleven. Okay, we can use this 7-Eleven. Okay, we have output here, capital and labor. Okay, let me show you how to calculate this this table 7-Eleven. Okay, 7-Eleven. Okay, we have the data 7-Eleven. Okay, this is the data 7-Eleven. This is the data 7-Eleven. Okay, then let me show you how to calculate this 7-Eleven by using Shazam. Okay, okay, I copy this one, this variable. Okay, we have 27 sample. Okay, we open the Shazam here. Okay, okay, I delete this one. Okay, samples 1 to 27, right? Read output Q, and the Q is capital, and label. Okay, this is the data. Okay. Okay, we estimate the OLS. No, we calculate this. Okay, first we generate one. One is the first column of the variable. We copy here. One is the first column of X matrix, and Q. Sorry. K and L become X. We copy Q become Y. So we create matrix XX is X prime X. Matrix X inverse is inverse XX. Matrix XY is X prime Y. So we can calculate matrix beta is equal to X inverse multiplied by XY, and we print the calculation results is XX, X inverse, XY, beta. Okay, we get the value of each variable here. Can you see this one? We have sample 27 samples here, and we have sigma x1 is a sigma of capital 5313 point something. This is a sigma labor is 23299.4 and etc. This is singular metric because the value of A12 is equal to A21 here. A12 here, element A12 is equal to element A21. Okay, and element 13 is equal to the element 31, and element 23 is equal to the element 32. This is singular symmetric matrix. Symmetric matrix means the sum of the off diagonal value of diagonal are the same. Okay, this is the symmetry matrix. Okay, this one x prime x inverse. Okay, this one x prime x inverse, and then we have x prime y. We calculate, we multiply x inverse x prime x with x prime y, we get the betas. Okay, this is the value of betas. Beta 1 is minus 135 something. Beta 2 is 0.011. And beta 3 we have 0.26 something. Okay, this is a calculation with matrix. We also can estimate directly by using the application, this software directly. Okay. Okay, we type here OLS. First must be the dependent variables. The dependent variable is Q here, and followed by independent variables. Okay, if you have 5 independent variables, that means you write down 5 dependent variable here. And you have here options. We can make, for example, R stat. That means you produce statistic of the regressions, or you want to produce other statistics. It's up to you. Or if you type here max, that means you calculate all of the statistics, even though you do not need the statistic in your thesis, for example. Yeah. Okay, we run this data, we get the estimated result here. Okay, here the estimated results. Okay, you can compare the betas from here, from the matrix approach here, copy here, these betas, with the beta from the software directly. Okay, we can get here. Beta 1 is the same, 135. Okay, here. Okay, same is here. Beta 2, we get 0.0. We also get here 0.011 something. We have beta 3 is 0.26 something. And here we have p-value. Here p-value. Okay, here k is not statistically significant, and L is statistically significant and theoretically significant. Okay, sometimes we need to transpose the data into logarithm in order to get the best estimated results of the equation. For example, here, if you want to estimate in a logarithm, we transform the data into log term. Okay, LQ is equal to log Q here. Then LK is log K. It's a capital here. Then LS is a log of labor, and we estimate the equation, the production function is equal to ln. Okay, for example, you take the option of maximum, and then we get here the log term. Okay, this is the first estimated equations here with the log. We get the value of capital is not statistically significant because, oh sorry, T ratio here. Okay, this one T ratio is small, very small. The p value is 1 or 0.763 is greater than 0.05. This means this capital is not statistically significant, different from 0. Whereas the alpha for the coefficient of labor is statistically significant. Okay, compared to the equation in terms of logarithm, yeah, we have is a logarithm. Yeah. Also, we get the coefficient of capital is not statistically significant, different from 0. This means after transforming the data into log terms, the estimated result also, especially for capital, is not statistically significant, different from 0. But the labor is statistically and theoretically significant. Any question here? Do you have question? No question? Okay, sure. If you have question, you can ask me. I will explain for you. Don't worry. Be happy. No any question? No?
No, sir.
No, sir.
Not yet, sir.
Did you get it?
Yes, sir.
Inshallah.
Okay. Okay. I am not sure if you can get this one. Okay. Okay. Here, if we look at this equation, labor output per hour labor, this means this capital labor ratio. Okay, you can calculate this by dividing the output with the labor and capital with labor. Okay. Okay, we have equation 10, 11, 9, 7, 10. 7, 10, yeah. You can estimate the demand for money, yeah. Same thing. You can estimate by using this software. Okay, you can use Shazam, or you can use FUs or other kind of software, econometric software, especially econometric software. Okay. No any question? No. No question? No problem. Okay. Now I want to show you how to estimate this one by using this data view. Okay. Okay, yeah, variable 1. Okay, let me show you. This is Spss. Okay, we change the name here, become output here. Output. This is capital. Capital, another one is labor. And decimal is 0. No need long decimal here. Okay, and then we can estimate the equation of production function here. Choose analysis, and you have regression here, linear regression, the option here, linear regression of the automatic linear modeling. Okay, choose dependent variable. We have output here for dependent variable because we have two independent variables. Okay, here we have the capital labor. If you have to calculate in confidence interval, covariance matrix, turbine Waxan, and R square, okay, you can choose from the option. Okay, here if you use probability F here, okay, exclude case list wise. Okay, we have only two variables here, no need to choose likewise regression model. Okay, this is same. Okay, we get same coefficient. Labor is statistically significant. Capital is not statistically significant. Okay, if you want to run by FUs is okay, by SPSS is okay, or by SASAM is also okay. Okay, no any question? Yeah. No question, no problem, and no understanding.
Are we going to like have a discussion on how to use some of these softwares like more?
I hope the pandemic finish in this coming week. We can learn in the class. I teach you how to estimate by using SPSS, for example, or SASAM, or by using FUs. Okay.
Yeah.
Okay. But it is impossible to teach you in the class. We are not allowed to come to the class. Okay.
Yeah.
Hopefully, this coming October, everything is settled. We can learn directly in the class. I will teach you how to use all of these softwares. Okay.
Thank you.
Okay, no question, no problem, no understand.